right, so hello and welcome. Howdy. Let's see how this goes. I'm gonna take a moment here to check and make sure this is working before I go on to the next thing. Just give me a moment or two here. Hello, hello, hello. Check and make sure this is working. Sweet, it's working. Okay, cool. All right. So continue here. Let me go ahead and begin. So I'm gonna try to do a couple hours here of working on some problems. See how they go. Some buffering here. Okay, let's try it. So you are given a string S of even length consisting of digits from 0 to 9 and two integers A and B. You can apply either of the following two operations any number of times and in any order on S. Add A to all odd indices of S, 0 indexed. Digits, okay, so you start with even length string, digits 0 to 9, and two integers A and B, okay. So you're going to add A to all odd indices, 0 indexed. Okay, digits post 9 are cycled back to 0. So okay, so it's A mod, I feel like I've done this before. Oh, did I? Hold on. Oh yeah, this is I think I wanted to skip this one because it's the solution that I came up with for this is a little bit complex. Let's see, hold on. Yeah, I don't actually want to solve that one just yet. That one, the solution I came up with is really involved. These ones also are kind of involved, and I don't really want to do them just yet. I want to do them in like another time when I'm ready for it, I guess, when I'm up for it. Yeah, that one's a little bit involved. Well, let's just read it again, just for the sake of it, actually. I might come up with something different now that I'm looking at it. So, okay, odd indices, you can add A, and it'll be like mod 10. Or you can rotate the string to the right by B positions. And so you can add A any number of times, and you can rotate S to the right and B positions any number of times. Okay. And end in any order. Okay. And I need the lexicographically smallest string that I can obtain by applying the above. I think actually, I think I could use a greedy algorithm for this. I was going to use a different kind of algorithm, but I think a greedy algorithm works fine. I had a really hard time thinking about this question the first time I saw it. I don't know why. I really struggled for some reason. So let's see. Interesting. So yeah, it's only been a few minutes here. Okay. All right. Yeah, so I think a greedy approach is probably the way to do it. So what you'd want to do is you could cycle lexicographically smallest means you want to take the digit, I guess a digit that you could put in front, you want to make it as small as possible. So try to get a digit 0 in the first position. And then try to get the next smallest digit in the next position. There might be more than one way to get 0 in the first position, though. Okay. Let's see some examples. So 5525. A is 9, B is 2. So I could add 9 several times. Now, the problem with this, though, is that you're going to add it several times to all of the odd indices positions. So let's see. So it's the way they said 2050, and they said we're going to rotate to 2555 and add 9 to the zero indexed odd positions. Or the odd positions. Okay, not the even positions. Okay. So it's going to take down to 4, 3. Okay, then rotate again to now rotate 2 positions. So 2, 5 comes up. Okay. So this 2, 3, 5, 3 becomes 5, 3, 2, 3. And then now these 2s become decremented down to 1s. And then rotate again, and these 1s can be pushed down to 0. And we can't do anything that's smaller than 2050. Okay. So it looks like we could just take this from 5525. These 9s, you could apply it all the way down to 43210, get 5020, and then rotate and get 2050. And because the rotation is even, when you rotate it, it doesn't change the values that are being modified down, that are being modified by A. So, and not only that, it's already the optimal rotation given those values. Okay. Let's see another example. A is 5, B is 1. So here we can rotate wherever we want, but the problem is that if you add 5, 5 mod 10 has this property where 5 plus 5 is 0. It's gonna flip between 0 and 5. There's only 2 possibilities for each of these, which means it's either going to be a 7 or a 2, and this is either going to be a 4 or a 9. And 2 is smaller than both 4 and 9 and 7. And so you're going to pick 2 and 4, put the 2 in front. So 7, 4, rotate, becomes 4 and 2, rotate again, 2, 4. Okay, interesting. How about another example? This is already lexicographically smallest. Unless you could change these 1s to 0s. But let's see, 4 has a GCD of 2 with 10, which means that you're only going to get 5 different possibilities with 4. So 4, 8, 2, 6, 0. So you're going to cycle back after 5 possibilities. 1s, so this is already pretty optimal, but the ones maybe can go to something interesting, but the 5 states you would get is basically you would add 1 to all those 5 states. So that's 0, 4, 8, 2, 0, 4, 8, 2, 0, 4, 8, 2, 6. Becomes 1, 5, 9, 3, 7, which 1 is already the smallest of all those possibilities. So, yeah. And then rotating obviously is not going to make it better and improve it. Okay. So I was trying to figure out a way to do this that's more efficient than like a brute force. I actually was struggling to solve this at all, but previously, actually. Yeah, this is an interesting question. I kind of got stuck on this one before. I didn't want to go over it before. So let me think here. So I could do. I'm thinking of maybe there's a greedy approach. So let's think about B for a moment. So A, I can characterize the possibilities for the string basically as the different states. Take the GCD of A and 10, and that tells me how many states there are that are possible. When applied to the odd, basically the every other digit, and what those numbers will be with that applied, each of those states, it's just going to be, you just add this amount to each of those states. So 9 and 10 has a GCD of 1, which means it'll cycle through every possible digit so that you can actually get every possible digit from 5 from your starting point. The main issue here, though, is that there's two things. Firstly, because this is being applied to the odd positions and there's a rotation involved, there's two possible things that could happen. Number one, the rotation doesn't actually move any of the even indices positions into an odd position, meaning if B is even, which means the only possible choices you have are going to be exactly what I described, where there's those different possibilities for A, mod 10, A times X mod 10, whatever you want to call it. Certain number of times you add A mod 10, and then that applied all the way across to all of the odd values. Now you might be able to rotate around a bit, but if you can never exchange the evens and the odds, in other words, if B is even, then you're only ever going to be dealing with those elements that could be modified. The other elements are basically static, which kind of simplifies the logic a lot, because I think you basically would try to find. I think a greedy approach works really nicely in that case. In that specific case, I think you would. I guess you could just. I'm not sure actually about that. I have to think about that a little bit more. But I want to say there's a greedy approach there that works reasonably well, which would just be like basically just keep applying the rotation several times until you get the optimal approach, something like that. Like, it's not quite that. I want to say you could do a greedy approach there. I'm not quite seeing it, but I'm thinking like if you could only modify the odd values and there's only a finite number of states that it could be, or the odd indices, then the tricky part there is, like, you might think like, okay, well, just get the smallest value you can furthest to the left, right? And that almost works, except because you can rotate things, and I think we said this is even, right? The string is going to be even. So that does kind of simplify that case too. So suppose B is even and S we know is even. Tricky thing there is because you could rotate it, it's more like you're looking for the smallest lexicographical sequence contained in those possibilities, because you could always basically rotate that all the way to the left. Like whatever smallest value you get, you could always rotate it to the left, the furthest to the left. And so I guess you kind of need to go through all those possibilities. There's not going to, like I said, there's only going to be about 10 of them. And the string itself is relatively small. It's only 100 characters. So you have 10 possibilities when B is even. maximum, and each of those possibilities, you could basically rotate any starting point to the beginning. And you want to get the smallest one. You want to get the optimally smallest one, which I think is, I'm not actually sure the best way to do that. And maybe you could scan left to right and then just say, to find the correct rotation point. It might be, the issue with that scanning is that the values could be equal. So there's like, you can compare like the current best with what you're looking at the moment. It's kind of like a prefix. It's kind of like a prefix type comparison. Makes me think of like a z function. So you've got like some lexicographical point or lexicographical string from left to right that is like basically the starting rotation, the sort of the selected rotation point, initial rotation point. And then as you see more characters, you append them to that string, but also consider maybe this is a new starting point for a potentially better string. And what's tricky about that is first off, there could be multiple instances that could be better, like simultaneously. Like in other words, if you had just a string of all the same character, for example, any rotation point there is going to be as good as any other rotation point, but you wouldn't know which one's the best because it could be that somewhere in that string there's another character like an X, in which case, like if it's all A's and an X somewhere in the middle, you'd actually want to rotate that X all the way to the right side. It's not as easy as just sorting these things. Like ideally you could just sort this, but it doesn't work like that. Just given any string, like how would I best, let's ask that question. Let's do that. That's a good question to ask. That's a good like kind of secondary question to ask. Let's suppose I have a string. Have a string digits s. I want to rotate the digits such that the rotated string is the lexicographically smallest possibility of all rotations. Do you understand? Like I could think this through, I'm sure, but I don't know what the best way to do this is. I don't know offhand. Is this working? Oh, okay, something happened there. So that's my thinking. Is maybe did this work? Okay. All right, string S, you want to find the lexicographically smallest rotation of that string. It's a classic problem often referred to as finding the minimal string rotation or lexicographically minimal string rotation. Problem defined. Yeah, see, I should know this, but I'm not, I don't know. Okay, we'll just read. String S of length n, there are n possible rotations, including the original string. You need to identify the rotation that comes first in dictionary lexicographical order. Rotations, lexicographical order. There you go. 1, 4, 3, 2. Okay. Efficient solutions. While the naive approach checks all n rotations in quadratic time, there are optimal algorithms that solve this in linear time. Booth's algorithm. Use a modified version of the... that's what I was thinking. I was going to say, there's like I'm thinking prefix cut type of thing going on. KMP, there you go. Preprocessing function to find the starting and could I use a Z function instead of the KMP preprocessing port? Yeah, I bet you could. The KMP algorithm and the Z function kind of resolve similar things, just in different ways. And a lot of times you can use them not interchangeably completely, but you can kind of modify them and interchange them in that sense. Find the starting index of the minimal. I was thinking that. I was like, can I use a modified KMP for this? Booth's algorithm. Okay. Duval's, often used for Linden factorization, which I don't know what that is. What is Linden factorization? Linden factorization. Can also efficiently find the minimal rotation by concatenating the string to itself and finding the smallest substring of length n. Interesting. Would you like to see the implementation of one of these algorithms in a specific programming language? Yes, you can use the Z function to solve this problem, but it's not as direct or as standard as Booth's algorithm, which uses KMP. How works the Z function? The standard approach using the Z function involves binary search on the length of the common prefix, making the complexity n log n rather than the optimal O of n for Booth's or Duval's. Okay, we're not going to go over that. Revised strategy, string hashing of suffix array, the actual. Okay. So anyway, okay. Would you kindly explain Booth's algorithm and Duval's algorithm? Linden factorization is a unique decomposition of any string into a sequence of Linden words arranged in non-increasing lexicographical order. Definition and core concepts. A Linden word is a non-empty string that is strictly lexicographically smaller than all of its non-trivial rotations. Oh. Equivalently, it is strictly smaller than all of its proper suffixes. For example, AB is a Linden word, but BA and AA are not. Okay. Chen-Fox-Linden theorem states that every string S can be uniquely factorized into a sequence of Linden words, such that S is equal to W1, W2, W sub K, where W sub 1 is greater than equal to W sub K, all the way down to W sub 1, W sub 2, all the way down to W sub K, lexicographical order. Uniqueness, the factorization is unique for any given string, small suffix, the last factor W sub K in the sequence is guaranteed to be the lexicographically smallest suffix of the original string S. Connection to minimal rotation. This property is directly useful for finding the lexicographically minimal string rotation. If you compute the Linden factorization of the string S plus S concatenated with itself, the minimal rotation corresponds to the Linden word that starts at the beginning of the last factor of the original S within that expansion. Duval's algorithm. The factorization can be computed in O of n time with constant extra space using Duval's algorithm. The algorithm iterates through the string, maintaining pointers to identify the longest possible Linden word prefix at each step, effectively peeling off Linden factors from left to right while maintaining the non-increasing order constraint. Okay, interesting. Okay, so this is part of the reason why I was struggling with these questions, because I was basically going to reinvent one of these two algorithms myself. I was like, let me come back to this. I was thinking of a KMP. I was literally gonna reinvent the Booth's algorithm, and I was like, I don't know about this, man. Oh, that's funny. Here's an explanation of Booth's algorithm and Duval's algorithm, both of which solve the lexicographically minimal string rotation problem in linear time. Adapts the Knuth-Morse-Pratt string matching preprocessing step to find the smallest rotation. Treats the problem as finding the best. I was going to say, yeah, so the reason why I thought of the KMP part is because you're doing prefix matching. Like that's the core of this, is that like I said before, if you had like all A's and an X somewhere in there, like you could try to compare each starting point to like your best prefix so far. And that basically is the same thing as the KMP algorithm, where the substring search does a very similar thing. We're trying to find um, some index that matches not necessarily the beginning of the string, but another string, right? You're trying to match it against another string. The issue with KMP you're trying to resolve is that the problem that you're trying to resolve is that instead of doing it naively, where you take every index and then try to match it straight across to your original word, what KMP allows you to do is basically discard a lot more indices much more quickly, because you can guarantee that those particular options are not going to be useful. The way KMP does it, it's actually kind of simple. The basic idea, it's more or less you use you pre-process the string you're looking for, and then you use that pre-processed string to actually perform the same maneuver, almost exactly the same thing. It's basically another pre-processing, same kind of algorithm on the larger string. So smaller string A that you're searching in B, that's the larger string. You pre-process A. What you do is you basically figure out which sections of A, when considered, have a prefix that matches a suffix. And then those sections themselves can be reduced further to potentially another prefix, another suffix. So it's sort of this like iterated prefix suffix thing going on, where the whole string has a prefix and a suffix that matches potentially, and then the prefix that matched that suffix itself then has a prefix and suffix that might match, and then that prefix might have a prefix and suffix that matches. And that's what the KMP table does. The pre-processing is you basically figure that out for each string, substring, really, each prefix of the your string you're looking for. You figure out what those sort of onion layers of prefix and suffixes are. The reason that's helpful is you can now, if you use that structure and you basically perform the same kind of routine on B, you effectively do the same thing. The reason that's really helpful is that you can instantly decide if you see a character that doesn't match. You can cycle through these different prefix and suffix possibilities very efficiently, very quickly, and figure out how much of the prefix you should keep when you see a character that doesn't match. Whereas previously in the naive approach, you would not know anything about the strings you're working with, and so you'd have to just assume at every index the entire string could be a match. And so if you have a failure point, you'd throw out all of the previous work you already did, and start over. And it's very inefficient. Whereas with the KMP table, now you can actually you basically cycle down to figure out how much of the prefix that you've already processed you should keep while you keep going. And this allows you to, you could prove that the cycling downwards is efficient. Like there's a way to show that you're never going to cycle downwards like too much, so to speak. Yeah, something like that. I have to remember exactly what the proof is, but it's something to that effect, where you keep some portion of what you've already pre-processed, and the KMP table allows you to prove that like you don't need to throw out more than that, and you can't keep less. You can't keep more than that, and you don't have to keep less than that. Or excuse me, you have to throw out at least the amount the KMP table tells you to throw out, but you don't need to throw out more than that. So it's like exactly the amount that you need, and it jumps to it very quickly. And I think, you basically won't perform more jumps than I think the part of the proof is that you can't perform more jumps downwards than you have characters in the string. That's what it is. Yeah. So yeah, basically that's so that basically forces the algorithm to be linear time. Yeah, something like that. Something like that. That's more or less KMP algorithm explained in plain English. So why is it relevant here? Well, we're doing a very similar, we're trying to compare all of these different indices and the prefix involved to like an optimal kind of prefix rather than it's a little different. It's not just a single prefix. It's sort of like if you were to do a substring search, but you keep changing the substring that's being searched. So a variation of KMP is kind of what I was thinking, but yes, this is someone figuring this out in the 80s. That was a long time ago. Excuse me. Interesting. All right. So pre-processing step to find the smallest rotation. Core idea treats the problem as finding the quote-unquote best starting position in a doubled string by maintaining a failure function similar to KMP's pi array. Instead of just matching a pattern, it dynamically updates the starting position of the candidate, minimal rotation, whenever other lexicographically smaller character is found. Mechanism can concatenate form S plus S to handle circularity linearly. Modified failure function, it computes a failure array F, where F of I stores the length of the longest proper prefix of the current candidate rotation that matches the substring ending at I. Dynamic update. As it iterates through T, if a mismatch occurs between the current character and the candidate rotation, if the current character is smaller, the algorithm shifts the candidate start position forward to the current index, discarding the previous candidate as suboptimal. Now, what's interesting is when the current character is equal to the other character's previous candidate's starting point. If the current character is larger, it uses the failure function to skip ahead, avoiding redundant comparisons, just like KMP. Interesting. Runs in linear time, uses linear space of the failure rate. It performs at most 3n comparisons. Duval's algorithm. So we'll implement Booth's KMP-based algorithm. We'll come back to that. Proposed by Jean-Pierre Duval in 1983, this algorithm relies on the Chen-Fox-Linden theorem regarding Linden words. Any string can be uniquely factorized into a sequence of Linden words, w sub 1, w sub 2, to w sub k, such that w sub 1 is greater than or equal to w sub 2, etc. The last factor, w sub k, in this factorization of S plus S corresponds to the start of the lexicographically minimal rotation. Mechanism, concatenate to T equals S plus S. Greedy factorization, the algorithm iterates through T, maintaining 3 pointers, start of the current factor being built, current character being examined, offset within the current periodic candidate. If T of j is equal to T of k, the periodic pattern continues, increment j and k. If T of j is greater than T of k, the current sequence breaks the Linden property. It's getting larger, reset k to the start of the factor I. Continue extending, the current prefix is still a candidate for a Linden word. T sub j is less than T sub k, the current character is smaller, meaning the previous sequence is not the smallest. The algorithm peels off the confirmed Linden factors, advancing I, and restarts the search from the new, smaller character. The resulting index of the last Linden factor found within the first n positions is the answer. Runs in linear time and uses constant extra space, excluding the input string, making it slightly more space efficient than Booth's. Okay. Okay, understand. Summary comparison. Modified KMP failure function, Linden word factorization, time complexity is linear, space complexity is linear for the failure array and constant for the auxiliary. Skips mismatches using prefix data, greedily builds decreasing Linden factors. Slightly more complex logic for updates, elegant three-pointer loop. Both algorithms are optimal. Duval's algorithm is often preferred in competitive programming due to constant space requirement, concise implementation. While Booth's algorithm is a classic application of KMP logic. Cool. Whoops. It's great. Duval's is probably. If I understand this correctly, finding the last Linden factor, it also resolves finding the rotation point, because last Linden factor can be put front of the Linden factorization, which then yields the lexicographically smallest rotation. Is that fair? I think that's accurate. I think it's like almost a direct result. Slight clarification on the mechanism. You don't exactly move the last factor to the front manually. Instead, the starting point of that last Linden factor within the concatenated string is the rotation point. I mean to say, that is why that is the rotation point. If I were to move the factor to the front, and all of the other possible rotations necessarily lexicographically smaller, because that Linden larger, that Linden factor is the smallest. So that that is okay. Precise reason relies on the non-increasing order of the factorization. Here's the refined logic. Smallest suffix property, the last Linden factor in the factorization is the lexicographically smallest suffix of the string among those starting within the first n positions. Non-increasing sequence, since the factorization produces w sub 1 greater than equal to w sub 2 all the way down to w greater than equal to w sub k. The factor w sub k is smaller than or equal to all preceding factors. Y rotations are larger. Any rotation starting inside a previous factor will begin with the suffix of w sub I. Since w sub I is a Linden word, it is strictly smaller than any of its proper suffixes. Thus, a rotation starting mid w sub I is larger than starting at the beginning of w sub I, and since w sub I greater than equal to w sub k, that rotation is also greater than equal to w sub k. Ah, okay. Okay. Starting mid factor will also have a similar property starting with a given factor. Isn't the smallest. Isn't so there's that. Yeah, that's pretty important. Okay. Any rotation starting at a previous factor begins with w sub I. Since w sub I is greater than w sub k, this rotation is lexicographically larger than or equal to, in the case of periodic strings, the one starting at w sub k. So by moving w sub k to the front, you are effectively aligning the string to start with the globally smallest valid prefix, ensuring no other rotation can be lexicographically smaller. That's amazing. So this part, any rotation starting inside a previous factor will begin with a suffix of w sub I. Since w sub I is a Linden word, it is strictly smaller than any of its proper suffixes. Thus, a rotation starting mid w sub I is larger than starting at the beginning of w sub I. Since w sub I is greater than equal to w sub k, that rotation is also greater than equal to w sub k. That's amazing. That's really cool. That's amazing. So Linden factorization and Duval's algorithm. That's crazy. That's crazy, man. That's crazy. So I could use Duval's algorithm with all the different possibilities. Sort of. There's something special here, though, where there's actually something here that's important. It's 5 a.m. I woke up to drink water. I want to sleep some more. Kid with a hard work, carpe diem. Hope things are going well for you. What's up, Yash? Hope your day's going well. Welcome, welcome. Howdy, howdy. I wanted to ask you, I'm not sure if you're still here, but I wanted to ask you about your interviews and whatnot, if your things are going well. I had asked, you had made a comment before on a video, and I asked about it, and I was like, oh, I hope it's doing okay. I kind of wanted to keep up because interviewing is hard. Interviewing is hard, and having someone kind of encouraging you is definitely a positive thing. Helps. Um, and vice versa too. If you could encourage someone else, it's also a positive thing. This is pretty cool, man. This is pretty cool. So this doesn't exactly translate to this problem though. There is a variation point that's important. So I probably would need to modify Duval's because, so for sure, if B is even, there's only at most 10 possibilities for strings to work, to work through. And so I could just work through those 10 strings directly using a variation of Duval's. But the problem here is that even though Duval's would be helpful potentially, I don't have every rotation point. I only have the even rotation points. So I would need to filter on only the even possibilities. In addition, I don't necessarily have the even possibilities. I have it's the GCD of the size of S and B is I would have to divide S by that GCD, and that would give me the number of rotation points that I could use. So it's not even just the even ones. They're going to be even, but there's also, or excuse me, they're going to be the sort of even points, even indices, I guess. In this case, not necessarily even, right? I think this one is odd. Yeah, it's 0 or 2. Oh no, it's even. Yeah, it's even indexed. Even indexed positions could be the ones, but also some of them, even though they're even, they wouldn't be available, right? So the positions themselves are also filtered by slightly. So I need to also filter on that. But I could just brute force in the even case, there's only 10 possibilities. In the odd case, there's 10 by 10, which is 100, at most 100. So it'd be 100 different strings, which 100 by 100 is only 10,000. If I process each of them in linear time. However, I need to use a variation of Duval's because I don't actually have every explicit point to work with. But presumably, I could use a variation of Duval's. Every factor of W sub I in decomposition is a Linden word. It possesses the property that it is strictly lexicographically smaller than any of its own proper suffixes. This means starting mid-factor. You start a rotation in the middle of a Linden word, W sub I, the resulting string begins with a proper suffix of W sub I. Since W sub I is strictly smaller than that suffix, the rotation starting at the beginning of W sub I is strictly smaller than the one starting mid W sub I. Comparison of the minimal factor, since we know W sub I is greater than equal to W sub K, where W sub K is the smallest factor. Any rotation starting mid W sub I is even worse, larger than starting at W sub I, and thus definitely larger than starting at W sub K. It's double-layered guarantee, Linden property within factors, and non-increasing order between factors ensures the start of the last factor is the unique global minimum or the first occurrence of the minimum in the case of ties. Cool. It's really is an elegant solution. The mathematical properties of Linden words, being smaller than their own suffixes, combined with a non-increasing factorization guarantee that you don't even need to compare every rotation explicitly. The structure of the string itself reveals the answer. Since you're ready to implement Duval's algorithm, would you like to see a code example in a specific language like Python, C++, Java? No, that's fine. That's fine. Could you explain Duval's for me? For me again. I am in need of a modified Duval's algorithm. However, that operates in such a way that I can only rotate the string by a certain amount, but I can do it any number of times. Are you with me? Are you with me? How am I doing with my it's a lot of buffering, I think, unfortunately. So okay. I wanted to see. Oh, so it looks like Yash left. He left by the time I read his comment. I'm with you. You want to find the lexicographically smallest rotation reachable by performing only small shifts, rotating by at most k positions at a time, but you can repeat this operation any number of times. No, I must rotate exactly k times, but I can do it any number of times. Subset of rotations, okay. With you, the constraint changes the problem from finding the global minimum to finding the minimum within a specific subset of rotations. If you must rotate by exactly k positions any number of times, the set of reachable starting indices from index 0 is m times k mod n, m greater than or equal to 0. Mathematically, this set consists of all indices, that's what I was saying, all indices I such that I is a multiple of g equals GCD of k and n. Yeah. GCD of Kn is equal to 1. You can reach all n rotations. The answer is the global minimum, standard Duval's. If the GCD of K of n is greater than 1, you can only reach indices 0, g, 2g, etc. You must find the lexicographically smallest rotation starting at one of these indices. Right? Modified Duval's log. Cannot simply run standard Duval's and hope it lands on a valid index. Instead, you treat the string as a sequence of blocks of size g. So the calculate step, compute this GCD. Conceptually divide the string S into M equals N over G blocks, where each block B sub I is the substring S I times G, I plus 1 times G minus 1. Okay. Rotating by K, a multiple of G, is equivalent to rotating the sequence of blocks by K over G positions. Since the GCD of K over G M is 1, you can reach any permutation of these blocks by rotation. Apply Duval's on blocks. Run Duval's algorithm on a sequence of blocks. Comparison when the algorithm compares two characters, which are now blocks, and compare the substrings of length g lexicographically. This takes O of g time. Complexity, Duval's performs O of m comparisons. The total time is O of m times g equals O of n. Space is O1 auxiliary. So it's still linear. G is 1, run standard Duval's. If g is greater than 1, initialize pointers on Duval's for Duval's on the block string of length m equals n over g in the comparison loop. Instead of comparing S of r and S of p, compare the substrings S of r times g dot 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 r times g plus g minus 1 and S p times g to p times g plus g minus 1. The result will be the starting block index I. The actual rotation point, the original string, is I times g. This ensures you find the smallest rotation reachable under your constraint. Oh, interesting. Okay, so because the rotation points are constrained, I can still break string to G sized blocks. All of those blocks are exactly incident on the potential rotation points. You can then abstract away the underlying string as blocks instead of characters and run the standard duvals on blocks with the modification. Blocks will compare to each other in their block specific way. Is that fair? That is exactly fair and is the optimal way to solve the constraint problem. Correctly identify the two key components, alignment. Since reachable indices are multiples of G equals GCD of K and N, the boundaries of your blocks G align perfectly with every valid rotation point. No valid rotation starts inside a block. Abstraction: by treating each block of G characters as a single super character, you can reduce the problem to finding the minimal rotation of a string of length N over G. Since you can rotate by K, which is a multiple of G, you can effectively reach any block alignment, making the block string fully rotatable. Implementation detail and running Duval's algorithm on this abstract sequence. Indices your pointers I, J, K, and iterate from 0 to N over G minus 1. Comparison: when the algorithm needs to compare two elements, say at block index A and block index B, perform a standard lexicographical comparison of the substrings. Result: if the algorithm returns a minimal block index, the actual rotation shift for the original string is I sub block times G. This approach maintains the linear time complexity because you perform O of N over G comparisons, each taking O of G time. Cool. That is very clear. All right. So Duval handles that very nicely. Okay, so there we go. That's probably the solution. It's going to be basically modified Duvals with the basically the GCD of A and GCD of A and 10 potentially squared. If B is even, it's just the GCD of A and 10. Different possibilities. And then if B is odd, then it's going to be the GCD squared possibilities. And it's actually going to be the GCD of, I think, 10 divided by that GCD. Oh, no, it's just the GCD. No, just the GCD, I think. I have to think about that for a minute. Let's say A is 8, GCD of 10 and 8 is 2. No, I think it's 10 divided by the GCD of those two. Because you do 8, 6, 4, 2, 0. Right, mod 10. Yeah. So that's 5. Yeah. You do 10 divided by the GCD of those two. Of A and 10. And then that could be potentially squared, and then you multiply that by the number of strings. Or excuse me, the size of the string, because they're going to run Duvals on each of those. So it could be like 100 by 100, which is going to be efficient. It's going to be fast. So that's, I think, the solution to this one. Like I said, I didn't really want to do this problem before because I actually didn't know Duvals at this point. I didn't even know about it. And I basically was going to come up with my own KMP variant to do the pretty much reinvent Booth's algorithm. It's interesting that they figured this out in the 80s. That's a long time ago. They figured this all stuff out. That's pretty amazing. It's actually really, really amazing. So that works. Okay. So could you walk me through Duvals again? Don't know that much about Linden factors nor Linden factorization. So this is a bit new to me. So yeah, there is, depending on whether or not B is odd or even, like I said, there could be at most 10 or at most 100 different strings to consider. And basically in the sort of the two, I guess the two canonical strings to work with are going to be, if B is odd, if B is even, then I can just take every odd index and add A, and each addition is going to, and take add A to each of those spots, mod 10, and each of those are going to generate strings that I can then apply the modified Duvals to directly, right? That's when B is even. When B is odd, I can access both the even and odd indices, and so the canonical string should be the initial string with A added at the odd indices, mod 10, but then rotate once and then add A to that section, however many times that needs to happen. So I think a single rotation on B is probably the right way to go, which would be, like I said, if B is odd, it's just a single rotation is the way to go. And that should be fine. That should be fine. All right. So let's learn about Duvals. Let's break down Duval's algorithm and the concepts behind it from scratch. What is a Linden word? A Linden word is a string that is strictly lexicographically smaller than all of its non-trivial rotations, cyclic shifts. Okay. It's a string that is strictly lexicographically smaller than all of its non-trivial rotations. So it's the smallest of all possible rotations. Okay. Now, what's interesting about the Linden word is that Linden factorization allows me to find the strictly smallest lexicographical rotation of the whole string. So that's pretty interesting. Basically, there's a kind of a recursive nature to it, where a Linden factorization breaks the word into Linden words, or breaks the string into Linden words, but the Linden word itself can use that lexicographical factorization to actually find the Linden word for that given string. That's very interesting. Anyway, so AB, rotations AB, BA, comparison AB is less than BA, solve AB is a Linden word. Counterexample, consider BA, rotations, BA is not a Linden word. Okay, another example, AAB, rotations AAB, ABA, BAA, AAB is the smallest, it is a Linden word. Okay. So the Linden word is its lexicographically smallest rotation point, or rotated string. Okay, got it. Key property, a Linden word is also strictly smaller than any of its proper suffixes. Okay, so any suffix of the Linden word is also necessarily going to be, so like AB is going to be larger, lexicographically larger than AAB. Okay, that's a key property. Why is it, comma, that a Linden word will always be strictly smaller any of its proper suffixes? I would guess the reason for this is, let's suppose it wasn't. That is, that there is some suffix that is lexicographically smaller. If that was the case, then I could rotate the prefix to append to the suffix, and that would break Linden property. Is that fair? I think that's right. think it's a fair, yeah, exactly fair, captures the core logical link between the two definitions. Correctly identify that if a word were not smaller than one of its suffixes, you could construct a rotation that's smaller than the word itself, violating the primary definition of a linear word. Proof logic. There you go. Reasoning proof by contradiction. Okay, got it. Ba-ba-da-ba. Strictly matters. Linear word must be strictly smaller, not equal. Right. Linear words are aperiodic primitive. If W were equal to rotation, it wouldn't be a linear word. Since linear words are strictly smaller, does that imply that periodic strings do not have linear words? I would assume so. Guess is correct. Proper suffix were smaller, rotating the prefix to the end would produce a rotation that is smaller or equal, breaking the condition that the original word is the unique minimum rotation. Exactly correct. Okay, periodic strings cannot be linear words. Wait. A periodic string cannot be a linear word, but can periodic strings have limits? I know that AAA, for example, cannot be a linear word, and no rotation of it linear word. Absolutely correct. While a periodic string as a whole cannot be a linear word, it can and always does contain linear words as its factors. In fact, every string, no matter how periodic, has a unique linear factorization. In the case of AAA, perfect for illustrating this. It's not a linear word. No, it's periodic, and its rotations are all equal to itself, so it's strictly not less smaller than them. Does it have linear words? Yes. Its linear factorization is simply AAA, where here the single character A is a linear word, has no non-trivial rotations, so the condition holds vacuous there simply because it's the smallest suffix. Periodic string is just the concatenation of three identical linear words. General rule for any periodic string S, equals W raised to K for where W is repeated K times, W is a linear word, the factorization is simply W K times. W is not a linear word. W itself is factorized first, and those factors are repeated. Key takeaway: periodicity prevents the whole string from being a linear word, but the string is always composed of a sequence of smaller linear words. Oh, interesting. For a given string that is not periodic, does it have a single linear word in its factorization? Oh, that is exactly correct. The string S has a string S has a linear factorization consisting of a single linear word, i.e. the factorization is just S itself, if and only if S is already a linear word. Oh. Logic: if S is a linear word, by definition cannot be split into smaller linear words. This violates the non-increasing condition. If S is not a linear word, if it's periodic, it must be broken down. If it is aperiodic, but not a linear word, it can be split into UV, where U is greater than equal to V. The algorithm will peel off at least two factors. Summary: single factor, the string is a linear word. Multiple factors, the string is not a linear word. I'm sure I fully understand. Hello. What's up, Loki? I think Loki may have left. But I would have said hello if I noticed it. Okay. Not sure I fully understand. I meant like for a given string, if it's not periodic, does that mean it's Linden word? Linden factorization is going to be just one Linden word. Further, in that case, it's optimal rotation. Lexicographically optimal rotation. However, for a periodic string, that Linden factorization cannot be a single word. Okay. So this is my thinking. No, that is not correct. Being aperiodic, not periodic, does not guarantee that a string is a single Linden word. Okay. Here's this distinction. Linden word implies aperiodic. Yes. String is a Linden word. It must be aperiodic, as we discussed. Periodic strings cannot be Linden words. Aperiodic implies Linden word. No. A string can be aperiodic, but still not be a Linden word. No. The Linden factorization of an aperiodic string. Think that must be a single Linden word, specifically the lexicographically smallest rotation of the string. Does that make sense? No, that is not correct. Being aperiodic does not guarantee that a string's Linden factorization consists of a single Linden word. Here's the precise distinction. The relationship between aperiodicity and Linden words. Linden word implies aperiodic. Yes. Aperiodic implies Linden word. No. No, you don't understand. The Linden factorization of an aperiodic string can't have more than one Linden word. Is that fair? I think it's not following me. No, that's not fair. It's a misconception, but is incorrect. Can have a Linden factorization with more than one Linden word. Okay, counterexample B. Is periodic? No. Can be formed by repeating a smaller substring. It is aperiodic. Is a Linden word? No. Linden factorization, since it is not a Linden word, it must be factorized into smaller Linden words. Oh, okay. I think I understand. Yeah, I was thinking Linden factorization included the rotation, but it does not. Find the Linden word associated with that string by using factorization. Factorization itself does not imply any rotations, not perform any rotations on a given string. Okay, I think I understand. Brother, how can I crack Fang understood from 0 in 5 to 6 months? I know DSA basics and Java. What's up? So I am saying. It's hard, man. Quite frankly, it's not that hard. It's not that hard. If you know like the basics, you could solve most of the problems. But there are things like what I'm going over here, like Linden factorization, which are very problem specific things. But broadly speaking, you literally can solve all of the LeetCode problems in like a month, maybe 2 months. There's a lot more problems now. Like that was like 4 or 5 years ago that I remember someone said they solved all the problems in like a month. If you just do all the problems that are like relatively easy, like you know the answers to, you solve them, and then you solve all the ones you know how to do, skip the ones that are too hard, and then either come back to the harder ones or just skip them altogether, quite frankly. But you could solve all the LeetCode problems in like probably about 2 months if you like really grind hard. But quite frankly, to really solve competitive programming questions, you kind of just have to learn the algorithms that are associated with those problems. Like this problem, for example, this is doing this optimally or efficiently, rather. Like you kind of need to know a little bit about efficient rotation points when dealing with lexicographical. The efficient way to find the rotation point that gives you the lexicographically smallest string among all possible rotations. And then actually the optimal solution here involves a variation of that too. So, or a couple variations combined, a couple of variants of this problem combined, a couple things combined, a variation of that combined with another like modification that the problem implies. So this is pretty like kind of a pretty unusual question, I would say. Like it's pretty out there as far as like computer science knowledge, like algorithmic knowledge. Linear factorization is a decomposition of the original string into parts w1 to w sub k, such that s is equal to w sub 1 to w sub k. It does not rotate the string. It simply cuts it into pieces while preserving the original order of characters. Okay. The string is still BA, just viewed as B followed by a rotation. How it helps to find the rotation. To find the lexicographically smallest rotation, we use a trick, which we'll come back to. Okay. So, very interesting. Now, here's the question. How is it proved that a given string always has a Linden factorization? Also, as previously discussed, some strings do not have an associated Linden word, but still have a lexicographically minimal string, rotated string rotation, long rotations. Have a lexicographically minimal rotation. Absolutely correct in both counts. Okay. Proof of existence, Chen-Fox, Linden theorem. The fact that every string has a unique Linden factorization is guaranteed by the Chen-Fox-Linden theorem. See, it might be a little harder for me to figure that one out on my own, come up with that Chen-Fox-Linden theorem on my own. That might be a bit challenging. The proof of existence is typically constructive and relies on induction or a greedy algorithm. Greedy construction: to factorize a string S, you repeatedly extract the longest prefix that is a Linden word. Let w sub 1 be the longest Linden prefix of S. Let w sub 2 be the longest prefix of the remaining suffix. Repeat until the string is empty. Okay. Pretty amazing. Chen-Fox-Linden theorem. Proof of existence is typically constructive and relies on induction or a greedy algorithm. Okay, greedy construction. So repeatedly extract the longest prefix that is a linden word. All right, W sub 1, then W sub 2, and so on. Okay, why it works. The key lemma in the proof is that if U and V are linden words, and U is less than V, then their concatenation UV is also a linden word. Oh, okay. Oh, interesting. So if U and V are linden words, and U is less than V, you can concatenate the two. It's lexicographically small, so you can concatenate the two, and it's still a linden word. Oh, that's very interesting. Huh. Yeah, since U is the smallest of any rotation, and V is the smallest of any rotation, if you just concatenate V to U, any rotation you have, that initial U is still going to be smaller. It's going to be smaller than any portion of U. It's also going to be smaller than any. Oh, I see. Oh, that's a very interesting dilemma. Since U is less than V, follows that any suffix of V is also smaller, larger than U, which implies UV is a linear word. I'm pretty sure that's the case. Not quite. No! Incorrect and not required for the lemma to hold. Oh. Whoops. Whoops. Incorrect and not required. What? Since V is a linear word, is strictly smaller than all its proper suffixes. So for any, we have V is less than S. Transitivity, U is less than V, V is less than S. It follows that U is less than S. So yes, U is smaller than a suffix of V. What? That's what I said. That's what I said. Why UV is linden. To prove, you must show it is strictly smaller than all its proper suffixes. Proper suffixes of UV are either suffixes of V, which we just showed, suffixes formed by a suffix of V alone. No, the suffixes of UV are of the form S. S is a suffix of V, or VU, V prime U. No, the suffixes of UV are suffixes of V and V itself. No. I'm kind of getting a little bit lost in what it's trying to express here. Crucial missing case. Actual lemma logic. Your statement is true. That alone doesn't prove UV. You also need to check the suffixes starting inside U. Well, suffixes that extend to U are also included by the fact that U is a linear word. And so those suffixes that are a part of U but extended by V are immediately less than U. Therefore, U must come first. Well, I was thinking about rotation points. To say UV is a linear word implies that it's the optimal rotation. Lexicographically smallest. Since all of the V suffixes smaller than V and then smaller than U, implies that none of those rotations put any part of v in front and be smaller. Further, smaller than uv. Further, if any part of u is put in front, then that also cannot be smaller than all of u in the front, because the suffix is u small or larger than u itself. Does that make sense? I mean, that's what I was thinking, something like that. Maybe it wasn't that obvious. Makes perfect sense. Correctly reconstructed the core logic of the proof by analyzing the rotation points, split points. To say UV is a Linden word means it is strictly smaller than any of its non-trivial rotations. Any rotation of UV corresponds to splitting the string at some point and swapping the parts. Core argument covers the two possible cases for that where that split can occur. Split inside V, putting part of V in front, let V equal XY, where X is non-empty. The rotation is Y is Yux. YUX, you argued since V is a Linden word, V is less than Y. Since U is less than V, U is less than Y. Therefore, the rotation starting with Y is lexicographically larger than UV. Conclusion, no rotation starting inside V can be smaller than UV. Split inside U, and U equal AB, the rotation is BVA. You argued since U is a Linden word, U is less than B, therefore the rotation starting with B is lexicographically smaller, larger than UV, which starts with U. No rotation starting inside U can be smaller than UV. All possible rotations correspond to a split either inside U or inside V, and you have shown that UV is smaller than the result of any such split. UV is indeed the lexicographically smallest rotation, thus UV is Linden word. Intuition about rotation points is exactly how the formal proof is structured. Cool. That's awesome. That's awesome. Yeah, that's a very clever lemma. So what was the proof again? Summary of the two key proofs we discussed: proof of existence, Chen-Fox-Linden theorem, proof that every string is a unique Linden factorization is constructive and relies on a greedy algorithm. So why it works: longest prefix would actually form a single longer Linden word, contradicting the assumption that W sub 1 was the longest prefix. If you pick the longest Linden prefix, the next Linden factor is guaranteed to satisfy W sub 1 greater than or equal to W sub 2. If W sub 2 were greater than W sub 1, then W sub 1, W sub 2 would actually form a single longer Linden word, contradicting the assumption that W sub 1 was the longest prefix. This process always terminates and produces the unique sequence W sub 1 to greater than or equal to W sub 2, all the way down to greater than or equal to W sub k. Concatenation lemma. Oh! The Linden factorization is almost a direct result of the concatenation lemma. Amazing. As you described, if the prefix was not the longest, then could be extended. If the prefix was the longest, then that implies the next word is necessarily lexicographically smaller. As mentioned, if it were not smaller, then it could be appended to the previous prefix, which contradicts that it was the longest. Oh, lexicographically. Almost a direct result of the concatenation lemma. Nailed the logic perfectly. The greedy strategy of Linden factorization relies entirely on that contradiction. precise flow. You pick W sub 1 as the longest prefix. Look at the next Linden word and the remaining suffix. If W sub 1 is less than W sub 2, then by the concatenation lemma, it would be a Linden word, but W sub 1, W sub 2 is a longer prefix than W sub 1. This contradicts the definition that W sub 1 was the longest prefix. Therefore, it must be that W sub 1 is greater than or equal to W sub 2. Simple logical loop guarantees that the greedy decomposition automatically satisfies the non-increasing order required by the Chen-Fox-Linden theorem. It's a beautiful example of how a local optimality condition, longest prefix, enforces a global structural property, sorted factors. That's amazing. Okay. So with the Chen-Fox-Linden theorem in hand, Linden factorization is actually rather straightforward. Proof of, and then how does Duval's take advantage of this? Could literally just find the longest prefix Linden words one by one. Maybe, excuse me, I could just find, okay. Okay, so that's the Chen-Fox-Linden theorem. That's pretty good. You could literally find the longest Linden prefix one by one, and that is exactly the greedy strategy behind the Chen-Fox-Linden theorem. However, Duval's algorithm in this is the specific, highly optimized implementation of that strategy that achieves linear time and constant space. How Duval's takes advantage. If you implemented the find the longest prefix idea naively, you might rescan characters multiple times, leading to quadratic time complexity. Duval's algorithm avoids this by maintaining a pre-simple state. I'm not sure what that means, pre-simple. Pre-simple strings. Instead of just looking for a Linden word, Duval's builds a pre-simple string, which has the form W raised to the K overline W, a Linden word W repeated K times, followed by a prefix overline W of W. Okay. Single pass. It uses 3 pointers, ijk, to scan the string once. I start of the current pre-simple candidate, J, current character being examined, K, the character in the candidate pattern we are comparing against. Efficient updates. If characters match or increase, S of J is greater than or equal to S of K, extends the pre-simple string. If a character decreases, it instantly knows the Linden factors are complete. It peels off all completed factors of length J minus K in one go and jumps I forward, skipping the recomparison of those parts. Find the longest Linden prefix, cut it off, repeat. This is the logical definition. Duval's algorithm, this is the efficient engine that executes your idea. It cleverly tracks the periodic structure so it never has to backtrack or rescan characters unnecessarily, guaranteeing linear time. Duval's literally doing exactly what you said, just with a clever pointer mechanism to ensure it takes time. Okay, interesting. Would I still need to scan left to right? Imagine that the first Linden word from right to left might very well be the W sub K that I'm looking. What do you think? Huh. Yes, you're absolutely on the right track. In fact, scanning right to left is a valid and often more direct approach to your specific goal, finding the lexicographically smallest suffix, which corresponds to the small start of the minimal rotation in the right to left approach. While Duval's algorithm scans left to right to produce the full factorization, you can find the last factor, W sub K, the one you need, more directly by scanning from the right. The goal, you want the lexicographically smallest suffix of the string. In the Linden factorization, the last factor is guaranteed to be the smallest. The algorithm, instead of factoring the whole string, you can simply find the starting position of the minimal suffix. This can be done in linear time by maintaining the starting index of the best suffix found so far. As you iterate backwards or using a specialized two-pointer scan from the right, a common linear time algorithm for this, often attributed to Duval as well, or simply minimal suffix algorithm, works by comparing suffixes and skipping indices that cannot be the start of the minimal suffix. Okay, why it works for you. Since your objective is to find the rotation point, the rotation point is exactly the start of the lexicographically smallest suffix of s, or strictly speaking, the smallest suffix of s plus s, or s plus $, where $sign is a sentinel, or simply the smallest suffix of s. If we handle periodicity correctly, scanning to find this specific suffix is sufficient. You do not need to compute w sub 1 to w sub k minus 1. Left to right Duval's computes the entire factorization. Good if you need all factors. Right to left minimal suffix computes only the last factor. This is faster in practice, same complexity, less work, and simpler if you only need the minimal rotation point. So yes, looking for the first Linden word from the right to left is exactly the optimal strategy for your problem. Okay, great. How might that be done in practice? Oh. Uh-oh. Hold on a minute before I go on to the next thing. But the problem is, what is going on? Oh, oh. All right. To find the lexicographically smallest suffix, which gives you the minimal rotation point in linear time and constant space, you can use a simplified two-pointer algorithm often attributed to Duval, derived from the Booth-Shalowick-Vishkin logic. You do not need to implement the full factorization or scan strictly right to left. A specific left to right scan that filters candidates is more standard and easier to implement. Minimal suffix rotation point maintains the starting index best, the smallest suffix found so far. Iterates through the string, comparing the current best candidate best to the new candidate logic. Iterate from I from 1 to n minus 1. Compare the suffix starting at best with the suffix starting at I. To do this efficiently in linear time, use a pointer k to find the first mismatch. Okay. K reaches n, or the end, stop, they're equal or periodic. If s best plus k is less than s of I plus k, the suffix at I is larger. Current best remains. We can skip all indices between I and I plus k because they cannot be the start of a smaller suffix. A property of Linden words set I equal to I plus k. Suffix at I is smaller. Best equals I reset. Okay. Interesting. Key optimization details. Skipping indices. The crucial part that makes this linear instead of quadratic is the line I equals I plus k plus 1. If you find a mismatch at offset k, you know that no index between the current start and start plus k can be the beginning of the minimal suffix. This allows you to skip redundant comparisons, handling periodicity. If the string is periodic, this algorithm finds the first occurrence of the minimal rotation start. It uses only a few integer variables, so it uses constant space. This approach effectively finds the longest Linden prefix reverse logic in reverse, filtering out non-optimal starting positions in single pass. Does this move from left to right? Maybe it's slightly more efficient to move right to left. So that's really interesting. I hadn't considered that might be the case. Also, I think I'm starting to run a little bit. Starting to run into too much context. Not sure I have enough. Too much context now. Standard Duval's algorithm and the two-pointer minimal suffix algorithm I described both move left to right. However, moving right to left is indeed possible and can be slightly more intuitive for finding the minimal suffix specifically, though it doesn't asymptotically improve the complexity. Right to left approach. Instead of filtering candidates from the left, you can scan from the right end of the string towards the left, maintaining the starting index of the smallest suffix found so far. Initial best equals n-1, last character is the smallest suffix of the suffix, starting at n-1, iterate from I from n-2 down to 0. Compare the suffix starting at I with the suffix starting at best. Since we're moving backwards, we can compare character by character, s of I plus k versus best plus k. If s of I is less than best, s of best, the suffix at I is definitely smaller, starts with a smaller character, update best of I equals I. If s of I is greater than best, the suffix at I is larger, keep best. If s is equal to of I is equal to s of best, we must look further, compare, perform the comparison repeatedly. Okay, keep this linear. Cannot simply compare character by character naively, which would be quadratic. We need to use the fact that if s of I to s of I plus k is equal to s best to s of dots best plus k, and s of I plus k plus 1 is less than s of I plus k plus 1, then best becomes I. If the suffix at I turns out to be larger, you can sometimes skip indices, but the skipping logic is trickier from right to left than the jump forward logic of the left-right version. They're both linear. It's a very clean skip left to right mechanism, very clean skip mechanism that guarantees linear time. Right to left version requires careful handling to avoid quadratic worst cases. The left to right is generally preferred because the skip ahead is simpler to implement, correctly avoids deep recursion or complex state management when mismatches occur late in the comparison. Right to left feels natural for suffixes. The left to right scan is a standard approach. Okay. So in theory, there could be a right to left version, but in practice, it's significantly more complicated. Is that fair? It's fair. The right to left scan is conceptually intuitive. We're finding the small suffix, implementing in linear time and constant space is significantly more complex than the standard left to right approach. Right to left is harder, there's more complex, there's skipping logic with comparison depth. Okay. So walk me through the left to right version. Would you kindly? You can kind of see why I didn't want to do this problem. You can kind of see why I didn't want to do this problem. It's pretty involved. This is the question we're working on. Those of you wondering what we're looking at here. Let me see how much time I spent on this so far. I think approaching 2 hours. Okay. Standard left to right algorithm for finding the lexicographically smallest rotation, which is equivalent to finding the starting index of the minimal suffix of s plus s. This specific implementation is called the two-pointer or Duval-inspired approach. It runs in linear time and uses constant extra space. Okay. Two candidate starting indices I and j and a match length k. Start of the best is I. Start of the new candidate rotation is j. Okay, I'm going to try to implement this here as a subroutine. Oops. Okay. Const auto best rotation. Smallest rotation, I'll just say best rotation, and we're going to have constant string s. Yeah. All right. So two candidates, I and j, and a match length k. All right. Current best, start of the new candidate, number of characters that currently match between the rotation starting at I and the rotation starting at j. As we scan, compare characters at offset k from both candidates. If they differ, we eliminate the worst candidate and jump its pointer forward, because no index between the eliminated pointer and the mismatch point can be the start of the minimal. Can you explain the logic behind the jump? We'll come back to that. That's really important. That's like the key critical thing. Let's use a string BAC, conceptually work with BAC to handle wraparound, but we use modular arithmetic instead of actually doubling the string. Okay. So n equals 4, I is 0, candidate starts at B, candidate 2 starts at A, match length. So I, J, and K. We do best J and I and K. We'll do best I and K. We'll do it that way. So we're gonna do ints. Really, you could use the size T. I think, but we're gonna use it. So int best is 0, I is 1, K is 0. Okay. Compare S of I plus K mod N and S of J plus K mod N. All right. So in this case, the string is BAC, and we're going to compare B and A, and we say A is smaller, right? So we update best. Any index between I and I plus K, which is just 0, is also invalid. Okay. Update I plus K plus 1 to 1. So I caught up to J, we must ensure I and J are distinct, set I equal to max of I and J plus 1. No, standard logic if I equals J increment J. I becomes equal to J increment J. Current state, I is 1, J is 1. Okay, yeah, that's fine. K is 0. Okay. Now we compare A and A. They're equal. Now we increment K. Okay. And now it's A and C. Candidate AA is better than AC. J is limited. Update J. J reached N. We can stop if we only care about starts that are less than N, but let's continue logically or stop. The middle start is I. Loop terminates when one pointer exceeds N, or we have checked enough. The answer is min I, J. Okay. Huh. I think this is Python code. Huh. Interesting. All right, let me see if I can implement this. I think I understand. So for loop, best is less than N. It's given the size, and I is less than N, and K is less than N. So we're going to say bounce char current. We'll say, and we'll say possible or previous. Yeah, previous is going to be S of, we said best plus K, and current mod N. And this is going to be I plus K mod N. We say if previous is equal to current, then increment K and continue. If previous is less than current. Really should do it like this. So if previous is less than current, then we're going to update best is equal to I, and plus I. And then if previous is greater than current, excuse me, we have to skip K. I guess I plus K. Yeah, we actually keep K here, I think. Best equals I, and increment I. I think that's fine. Then if previous is greater than current, excuse me, it's the other way around. This one. Yeah, if the current position is better. If the previous position, though, is better than current, then I think K is 0. And maybe still increment I. No, we don't increment I. We actually increment all the way through K. Yeah, we add all those values of K to I, and then we add 1. Yeah. So we don't modify I here. We just modify I. If we find a better point, then we update best to I and increment I. The new target. Actually, I think this one, I'm not sure about this one. I think it's just a increment I. And then I'm supposed to return the minimum of best and I in this. Here, animals. Just give me a moment. This is probably not correct. Likely fail or run in quadratic time on certain inputs. It contains 2 critical logical flaws compared to the standard linear algorithm, often called the Duval-like or Sherlock-Bishkin approach. Missing pointer synchronization. Your code, when previous is greater than current, the current candidate best is worse. Set best equal to I, and then only increment I by 1. Problem, you failed to reset the match length to 0. More importantly, best and I are now adjacent. Best is the old I is old I plus 1. The next iteration will recompare characters you already know about, but with K potentially still large or inconsistent. Okay. When updating best, you must ensure I is at least best plus 1 and K is reset to 0. Standard algorithm treats best and I as 2 independent candidates. If one loses, it is discarded entirely and the winner stays while the loser jumps ahead. Okay. Inefficient jumping. Code, you do I plus 1 plus I. String like ba. Best starts at B. I starts at 1. Iteration B greater than A. Best becomes 1. I becomes 2. K is untouched at 0. Continues until a mismatch. Imagine a case where best keeps losing frequently. Real killer. Both pointers jumping. Okay, corrected version. So A greater than B. Okay. So the correct reasoning, so the correct logic will always reset K when the characters differ. Is that fair? Critical rule. Okay. Length K is broken. The algorithm must discard the loser, advance the pointer of the lexicographically larger rotation. Okay. Interesting. All right, this is what I'm going to change it to. Okay, I think I understand. So both cases are going to update. So best increments forward, K plus 1, basically. So this is, hold on, what? A is greater than B. Candidate I is worse. A is greater than B, A is less than B. And they said A is going to be best. Okay. And so they jump I forward. I equals I plus K plus 1. Yeah, that's what I have. And in both cases, I set K equal to 0. Now, what's tricky about this is basically if best equals I, increment I. That's pretty much sort of what's one of the things. Let me see. I think this is what I need to do. That is correct. Successfully implemented the standard linear two-pointer algorithm for finding a lexicographically minimal string rotation. Code works. Symmetric jumping, both best and I jump by K plus 1 when they lose a comparison. This ensures no index is checked more than a constant number of times. Resetting K, correctly reset K immediately after any mismatch, ensuring the next comparison starts fresh. Pointer distinctness. The check guarantees you never compare a candidate against itself, which is essential for correctness. Termination, the loop stops as soon as one pointer exceeds n or K reaches n, implying the string is periodically found the minimal period. The result correctly picks the valid starting index. This implementation is robust, runs in linear time, uses constant extra space as the standard solution used in competitive programming for this problem. Okay. So you could just use I and J. It's maybe a little easier to think about. But let me consider. So this case I think I got right, but I didn't realize that this case was a little bit different. Why does the best yeah, it's just a slight variation. Why does the best case jump all the way forward to best plus equals K plus 1 when previous is greater than current? I think this means So these suffixes for the k elements, they're assumed to be equal to each other, or they are equal to each other, until a certain point where they're not equal, right? And these are like two kind of substrings, I guess, that are being compared. S of best, that's the previous, so up to that, those k elements, that previous point, it's now larger, which means I need to take best and update it to I, which has all the same characters, but is now better. Now, what's interesting is that we update it, we just move best all the way forward. Why wouldn't I move best to I instead? Why can I move all the way forward? Yeah, this. Here's something. I think I actually need to. I think I'm not going to implement this. Just going to put this piece of code here, and then I'll probably take a break. You can jump best all the way to get best plus k plus 1 instead of just moving it to I because of a mathematical guarantee. No index between best and best plus k can possibly be the start of the minimal rotation. Here's a step-by-step logic. Setup: you're comparing two candidates. Candidate A starts at best, candidate B starts at I. They match for k characters. There's a mismatch at offset k. This proves candidate A is worse than candidate B, but why skip the indices in between? Partner argument. Consider any index P strictly between best and best plus k. An offset equal of D be P minus best. Okay, something between best and best plus P. All right. It's less than or equal to best plus k. Because the first k characters matched, the substring starting at P and A is identical to the substring starting at Q equals I plus D in candidate B. Okay, now compare the rotation starting at P with the rotation starting at Q. Rotation P starts. So that mismatch applies to all of the possible rotations between them. Compared to I. Is that fair? So that mismatch eventually will cause all of those to be very interesting. That imply can still be less than k plus best. Property still holds. Would guess that this also implies that I is greater than or equal to best these instances. Perfectly capture the core logic. The substrings are identical except for the very last character. Any rotation starting at an intermediate index will inevitably encounter the same larger character, the same relative position when compared to its partner rotation. Partner rotation is the smaller character at that critical mismatch. Every single intermediate rotation is guaranteed to be larger than its partner. None of them can be the global minimum, allowing you to safely skip the entire range. Intuition is correct. The standard algorithm I is always greater than or equal to best plus k plus 1 at the moment a mismatch occurs. Here's why. Initialization, matching phase. For the comparison to be valid and for the partner logic to hold without overlap issues, two candidates must not overlap in a way that creates a circular dependency within the current match length. Comparison to be valid and for the partner logic to hold without overlap issues, Two candidates must not overlap in a way that creates a circular dependency within the current. I'm sorry, I'm very distracted at the moment. Hold on, I probably need to go. There's, I feel like I have to explain. This is like pretty upsetting. These are not my animals. I'm not really supposed to be caring for these animals. But out of compassion, I've been taking care of these animals from time to time, sort of against my will, a little bit. I don't want to go into too much detail, but it's not a good situation. And unfortunately, you can hear the animals in the background here, so I feel like I have to say something, which is really frustrating. It's extremely frustrating. Yeah, the owners are not gonna go and give the animals attention for one reason or another, which is not good. All right, let me try to finish this. I'll just take a break. We'll just take a break. I'm pretty annoyed. I'm pretty annoyed. Yeah, it's not a great situation to be in. Eventually, I'll have to figure it out what I'm going to do. But anyway, so effectively maintained or established immediately after the jump, because if I were smaller, it would have been eliminated in the previous. So this seems to contradict what the AI was saying before, that I think my other algorithm might have been correct, but I'm gonna stop here. I'll pick this up later. Let me just say thank you for watching. I should get going. If you like the stream, don't forget to give it a follow. Give it a like if you like this kind of stuff I do, and you want to see more. If you're interested in subscribing, then don't forget to do that as well. If you subscribe, you can see more of my stuff. Yeah, thanks again for watching. Take care. Talk to you soon. And I won't program this now. I think I'm going to go through this again later, though, this algorithm, because I think my idea was correct the first time. Could be wrong. We'll come back to this. But yeah, this is a very interesting question. A lot of stuff to think about. And yeah, let me get going here, though, because there are things going on that I kind of need to